In this video, I will teach you about concavity and the second derivative test. The definition of concavity says, let f of x be differentiable on an open interval. The graph of f of x is concave upward on the interval. If f prime is increasing on the interval, it will be concave downward if f prime is decreasing. So hopefully at this point in the course, when you see f prime, you think slope. When you see derivative, you should be thinking slope. So this is saying if the slope is increasing, then the function, the graph, is concave up. If the slope is decreasing, the graph is concave down. So at a glance, you can see that this first graph is concave up, and you can just think to yourself, up. It's up in the sense that a smile is turned upward towards the sky. Some people like to say when you have a graph that is concave up, it would hold water like a bowl. Concave down is down like a frown. It's more of an umbrella, right? Water falls off of it. It doesn't hold water. But back to the actual definition, let's see why for the concave up graph, the slope is increasing. So let me draw some little segments that represent the slope. So over here on the left, you see we're starting out with a negative slope. And then if we go over a little bit more, this slope is still negative, but it's less negative. So that means it's increasing. Okay, as we move further over, okay, now the slope is beginning to become positive. And as you go even further, whoa, that's supposed to be a nice little straight line, but it wasn't. As we go over a little bit further, we see that the slope is getting steeper and still positive. So as we go from left to right, the slope is constantly increasing. All right, it starts off very negative, then it gets less negative, then it goes positive, then it gets more positive, and so on. So the slope is increasing, which means that the derivative is increasing. So that's what makes this concave up. Similarly, if you look at the second graph, we can see that the slope right here at the beginning is positive. And then if we go over a little bit, okay, we still have a positive slope, but it's less positive. So the slope is decreasing. Somewhere in here, the slope would be 0. Okay, I missed. But somewhere in here, the slope would be 0. Okay, I fixed it. And then if I keep going, then the slope becomes negative. And then as I go even more extreme, the slope becomes even more negative. So as you can see, from left to right, the slope is constantly decreasing. And technically, that's what makes this concave down. All right, the slope is decreasing, the derivative is decreasing. Before we do the first problem, let me mention to you that if you want to know how the derivative is changing, you need to look at the second derivative. If you take the derivative of the derivative, now you're examining how the derivative itself is changing, and that's what determines concavity. So that's why this lesson is all about the second derivative test. We're going to be taking the derivative of the derivative to examine whether or not the derivative is increasing or decreasing. Example 1, f of x equals 1/3 x to the third power minus x. Find the open intervals on which the graph of f of x is concave upward or concave downward. For concavity, ultimately we will need the second derivative, but that means first we have to find the first derivative. So f prime of x is equal to, and using the power rule, 3 times 1/3 is 1. Reduce the exponent, and we have x squared. The derivative of x is 1. So the first derivative is x squared minus 1. Keep in the back of your mind that this tells us if the original function f of x is increasing or decreasing. In other words, this tells us if the graph is going like this or like this. All right, I'm going to go ahead and find the critical numbers for the derivative. We won't need this to answer this question, but we will need it for a little bonus activity I'm going to tack on the end. So for the critical numbers, I'm going to set this equal to 0. There are no denominators, so I don't have to worry about where the function is undefined. I'm going to look at this as the difference of squares, so this would be x plus 1 times x minus 1 equals 0. And using the zero product property, I get critical numbers of x equals -1 and x equals +1. Okay, we will not need this for concavity, but it'll be for a bonus lesson. So let's go ahead and find the second derivative. So now we're doing the derivative of the derivative. So power rule will give us 2x, and that's it, because the derivative of a constant is 0. So we've just learned that the second derivative tells us whether or not the first derivative is increasing or decreasing. Or in other words, it tells us whether the original function is concave up or concave down. But first, let's find the critical numbers of the second derivative. So of course, we will set the second derivative equal to 0, and we come up with our one and only critical value of x equals 0. So for concavity, this is the only critical value that matters. So I'm going to ignore the two critical values from the first derivative. We will only need that for the bonus lesson that's going to be later. So since we only have one critical value, this is going to be a very basic graph. It should be relatively simple. So I'm going to put that critical number right here in the center. So of course we will need test values in each of the intervals that I have just created. So let's use a test value of -1. So we'll do a test value of -1 over here. And let's do a test value of +1. We'll do a test value of +1 over here. Okay, so we are doing the second derivative. So I'm just going to label my calculations with a little second derivative down here. So any calculations you see me do, they will be second derivative evaluations. So this will be pretty simple. If I evaluate the second derivative at -1, that's just going to be 2 times -1. Remember, all I care about is whether or not this is positive or negative. Obviously, this will be negative. And second derivative tells us concavity. So that tells us that in this interval from -infinity to 0, the original function is going to be concave down. Looking at the other interval, we would have 2 times +1, which obviously is going to be a positive value, which tells me that in this interval, the function would be concave up, okay, in this entire interval. So that is enough information for us to answer the question that we were asked. We have determined that the function is going to be concave up in the interval from 0 to infinity. and the function will be concave down in the interval from negative infinity to 0. All right, so that's the end. We've answered the question. But I'm going to go on and build on this. One of our overarching goals for this unit is curve sketching. We want to be able to take information like this and try to quickly get an idea of what the graph will look like. So based on this information alone, let's see what we can sketch. Now, anything we sketch with this limited information is going to be of a limited value because we don't know that the graph will truly look like this. All we know so far is what the concavity is doing. Okay, so from negative infinity to 0, we learned that the function is concave down. So let's go ahead and sketch a function that is concave down from negative infinity to 0. So here would be one example of what that might look like. Okay, so that would be concave down. And then the function is concave up from 0 to infinity. So if I continue, but now I'm turning to a concave up situation. Okay, so this would be an example of a curve that fits the information. That's concave up from 0 to infinity and concave down from negative infinity to 0. Let me toss in a vocabulary word right here. The point where the function changes from being concave down to concave up is called a point of inflection. Just for fun, let's go back and layer on the information we can get from the first derivative. So for the first derivative, we had critical values of -1 and +1. So I'm going to use that now. These happen to be the test values that I used before, but I'm forgetting about that, and now I'm turning them into critical numbers. So now I've got 4 intervals as I look at the first derivative, and I'm going to need 4 test values. So first of all, let me label this area as the first derivative, because everything I do up here is going to relate to the first derivative. And I'm going to do a test value of, let's see, I'll use -2 for my first test value. And then I will use -1/2 would be a good one to do. And then I'm going to do +1/2. And then I will do +2. Okay, so these will be my test values. And we are using the first derivative, which remember is x squared minus 1. Keep that in your mind. Okay, so that will make this -2 squared minus 1. And that's going to be 4 minus 1, which will be a positive value. And first derivative just tells us if the function is increasing or decreasing. So in this interval, the function is increasing. And now let's look at -1/2. So that would make -1/2 squared minus 1. So this would be +1/4 minus 1, which will definitely be a negative value. So the function is decreasing in this interval. How about +1/2? So that's going to be 1/2 squared minus 1. So that's 1/4 minus 1. Just like last time, this is going to be a negative value. So the function is still decreasing in this interval as well. All right, back-to-back decreasing intervals. So how about the final interval? Let's do our test value of 2. So that'll be 2 squared minus 1. That's 4 minus 1. That is a positive value. So the function is increasing in this interval. Okay, so that tells us that we are going to have a relative max in this interval. Okay, so we're going to have a relative max at -1, and we're going to have a relative min at +1. Let's go ahead and figure out exactly what those values are, because I really would like to improve on this sketch as much as possible. Okay, so let's find the relative max and the relative min. So -1. Now we're looking back at the original graph. So if we do 1/3, and then we have -1 to the third power minus -1. -1 to the third power is still -1. -1 times 1/3 is -1/3. Minus a negative is addition. So I have -1/3 plus 1. That is going to be 2/3. So that means we have a relative max at -1, 2/3. Okay, so let's go ahead and include that in the picture. So this relative max right here at -1, 2/3. All right, which means this is -1 right here. And then we have this relative min at +1. So let's do that calculation real quick. Let's find the y value. Okay, so that would be 1/3 times +1 cubed minus +1. Well, 1 to the third power is just 1. 1 times 1/3 is just 1/3. So we have 1/3 minus 1, which is -2/3. So we have a relative min at +1, -2/3. All right, let's go ahead and improve our graph. So this is a relative min at +1, -2/3. Okay, so notice how this fits the original sort of guess that we made based on concavity. In this case, it is fitting well with the increasing and decreasing intervals. Notice that we predict that the function will be increasing from -∞ to -1. So sure enough, this graph is rising from -∞ to -1. Okay, now remember our 2 intervals in a row of decreasing. In other words, the function should be decreasing from -1 to +1. So look at our graph. This is indeed falling constantly from -1 to +1. And then it was supposed to be increasing from +1 to infinity, and that's exactly what we see here. From +1 to infinity, the function is rising. Okay, let's finish this off with a glance at the actual graph. So here's what the actual graph looks like fresh off of Desmos. And when you compare this to our graph, I think you will agree that we pretty much nailed it.